2.5 Early quantum theory. Planck, 1901. Max Planck was performing black-body experiments in 1900 and he couldn't get agreement between experiment and theory for the black-body radiation produced. He could get good agreement, however, if he constrained his oscillator model to only allow changes in energy of minimal increment that was proportional to the frequency of the associated electromagnetic wave. The constant in this relation would become known as Planck's constant. We consider the black-body experiment in detail in the next section. 2.5. 1 Black-body model. The emissive power from a heated, radiating body depends on the wavelength observed and the temperature of the body, where E of lambda, T, is the energy emitted per unit time. In work in 1859, Kirchhoff 50 defined absorptivity, A of lambda, as the fraction of incident radiation of particular wavelength that is absorbed by the body, such that.
See the equation, where C is the same for all bodies. For the theoretical extreme of a black body, we will have A of lambda equals 1, and the discussion turns to determination of E of lambda, T, for this instance as a universal function, for all bodies as indicated. According to Kirchhoff, the implication of the 2nd law of thermodynamics in such a circumstance is that the radiation from the body be isotropic, homogeneous, and the same in all cavities at the same temperature, and also holding for each wavelength. Relation between energy density in a cavity and emissive power. Suppose we have emissive area dA and a volume element a distance r from the area, at an angle theta from the to the area. In spherical coordinates the volume element is. See the next equation.
The emitted energy in the volume element has differential. See the equations. To get the flow of radiation in time interval gradient t, we must integrate the volume element with dr going from 0 to c gradient t. Thus, see the equation. So, emitted energy density is. See the next equation. By considering the special case of a perfectly reflecting spherical cavity contracting adiabatically, where the redistribution of energy as a function of wavelength is caused by the Doppler shift on reflection, Wien is able to show in general there must be the form.
See the equation. The Wien result fits well for the high-frequency data observations with the empirical formula. See the next equation. At low frequencies, the theoretical form indicated by Wien is completely wrong and a new model for the physical behavior is needed. In 1900, Rayleigh derives what is now known as the Rayleigh-Jeans law. See the equation. The model giving rise to this result is built on the model of a simple harmonic oscillator. A simple harmonic oscillator that is in equilibrium with a thermal reservoir at temperature T will have average kinetic energy kT divided by 2, see Book 6, 20, for thermodynamics details. A modal decomposition of the electromagnetic field in the classical theory reveals that each mode has the mathematical form of a simple harmonic oscillator. If the classical thermodynamic law of equipartition of energy is applied, each mode having energy kT divided by 2, we can describe the energy density if we know the number of modes for an electromagnetic field confined to a cavity. A calculation for the latter premised on a differential formulation, and including a factor of 2 for the two polarizations possible in each mode, gives the above formula.
Faced with two mathematical forms, one good at high frequencies and one good at low frequencies, Planck in 1900 came up with the black-body energy density by use of an interpolating function with an adjustable constant h. See the next equation. When the function is made to fit the low and high frequency regimes, matching the functional forms above, the adjustable constant is fixed at the value now known as Planck's constant. See the equation. The total energy in a cavity of unit volume is then. See the next equation, where, see the equation, is the Stefan-Boltzmann constant. This result for total energy is computed on purely thermodynamic grounds in Book 6, 20. Aside from the derivation for the Stefan-Boltzmann constant, which from the quantum mechanic derivation above must have the form.
See the next equation, where k is Boltzmann's constant, and h over 2 pi equals 2 pi h. Note that Planck's expression for energy density can be written. See the equation, which has the modal density term with an average energy per mode term. See the next equation. Planck found that if the energy per mode was set at epsilon equals h of nu and he considered a Boltzmann probability distribution for system at equilibrium temperature T. See the equation. Then the resulting average energy density for the system is.
See the next equation. As indicated, the implications of this are that the energy per mode is quantized and is directly related to the frequency of the mode. It wasn't until 1905, Einstein photoelectric effect analysis, 51, however, that it would be understood that this also related the energy of a quantum or corpuscle photon of light at a particular frequency by the same relation in general. Leonard, 1902. Leonard's work with cathode rays began in 1888. He was the first to show that the energy of rays in the photoelectric effect was independent of light intensity. 52. Einstein photoelectric effect, 1905. 51. Consider a work function for a given material given by W, with the experimental relation at maximal observed electron emission kinetic energy, given by conservation of energy as energy of light quantum equals observed electron emission kinetic energy plus empirically determined electron escape work function plus thermal/inelastic energy loss.
This relation simplifies further when written for the special case of maximal electron recoil energy, where a mostly inelastic process has occurred, thus eliminating the thermal/inelastic term, to give the relation, for a given material under photon excitation. E sub max equals energy of light quantum, negative W. We also have the linear thresholding behavior in terms of the light quantum's frequency, which can be described with the equation for the photoelectric effect in the classic form. See the equation, where h is Planck's constant, and the result that light has energy quantized according to frequency, E equals h of nu. Planck found a quantization on light according to E equals h of nu allowed the black body radiation profile to be explained, where h was a nu, quantum, constant. In 1905, Einstein adopts the idea of a quantum of light, motivated by Planck's studies, to conjecture the relation now known as the photoelectric effect.
See the next equation, where 1/2 mv² is the kinetic energy of the electron, nu is the frequency of the illumination, and where W is the work function of the metal, and is of the order of several eV, where 1 eV equals 1. 6 × 10⁻12 power erg. There results the Planck-Einstein relations. E equals hv, p vector equals h over 2 pi k vector, since E equals pc. H equals 6.62 by 10⁻34 power JSEC and h over 2 pi equals h of slash 2 pi. De Broglie relation, 1923. 53. In 1923 de Broglie considers scattering of electrons off of a crystal lattice, and observes preferred scattering directions at odds with classical theory. As with Einstein's indication of a wave-particle duality, here he attributes a wavelength to the electron according to a similar relationship to Einstein's relation for photon energy, E equals h of nu, where here we have the wavelength relation for massive, particulate matter, lambda equals h of slash p, scattering off a lattice, crystal, with spacing between scattering sites a. For constructive interference on the scattering, the phase shift on the scattered wave must match the added distance phase shift. The extra distance traversed on scattering a wavefront goes as 2 asine theta, where the added phase for a particular wavelength is.
See the equation. This added phase for constructive interference must equal 2 pin. We thus have preferred scattering directions as observed. See the next equation. Existence of a 4-vector description on energy momentum. Let's now recover the special relativity results of rest mass energy equals mc to the power, and the existence of a 4-vector description on energy momentum. We will use an anachronistic argument by making use of de Broglie's matter-wave function relation between wavelength and momentum. See the equation. Recall, p equals h over 2 pi k, where lambda equals 2 pi divided by the absolute value of k. For light we thus have. See the next equation. For light, since we don't have nu equals 0, we don't have p equals 0, so the above equation is applicable to describe any energy state of light. For matter, excluding massless matter, if it exists, we have the momentum given by p equals mv, where v is velocity, and this can most certainly be 0, in a particular frame of reference, and thus have 0 momentum. Thus to say that.
See the equation. For matter is clearly missing a rest energy term. Let's have such a term consisting only of mass parameter m and constants. thus dimensional analysis suggests. See the next equation. Let's now guess a 4-vector formulation on energy momentum such that the energy scalar can be written as adding component-wise in quadrature. See the equation. Is this guess consistent with the standard low-velocity classical mechanics kinetic energy definition 16, as well as consistency with the required kinetic energy form consistent with Riemannian geometry 17, when seen in its variational context? First, consider the V is much less than C behavior. See the next equation. And dropping constant terms from the energy when used in a variational context, we have energy given as.
See the equation. Precisely as required. Compton effect, 1924-54. In 1924, Compton considers the scattering of radiation, light, off of electrons, residing in a metallic foil. When expressing energy conservation, use will be made of the 4-vector energy momentum described above. If the light scatters as a classical wave, with re-radiation of light off of electrons that have been forced to oscillate, there results a re-radiation intensity variation with angle that should go as. See the next equation. And without any dependency on the wavelength of the incident radiation. The observed scattering involves re-radiation at the same frequency as well as radiation scattering at a second frequency that is dependent on the scattering angle. Compton is able to explain this using simple rules of particulate matter scattering, where the light is treated as a photon corpuscle of energy according to Einstein's relation for the photoelectric effect and momentum according to de Broglie's relation. Let's denote the photon momentum with lowercase p and the electron momentum, initially 0, by uppercase P. Conservation of momentum gives P goes to equals P goes to prime plus P goes to the absolute value of P equals h of nu divided by C. Conservation of energy gives h of nu plus mc squared equals h of nu prime plus the square root of mc squared plus pc squared. With some algebra this becomes.
See the equation. Or see the next equation, where the Compton wavelength for the electron is. See the equation. Bohr, 1913. 55. Bohr eliminated the classical radiative collapse problem by saying that the energy levels of electrons in atoms are discrete, and that electrons can move between levels with emission or absorption of an associated quantum of photon energy. The nature of the discrete levels was such that the electrons were described as stationary waves that could exist at particular, circular orbits. 55. This is equivalent to a quantization on angular momentum in the model. The model would recover the Balmer-Rydberg formulae and other observations as well as make many accurate predictions. 2.5. 2 Bohr model. Recall that for a classical orbit in a central potential we have. See the next equation. For the classical circular orbit on a hydrogenic atom. If we then add a quantization condition on the angular momentum in the orbit.
See the equation. We arrive at the stable orbit descriptions with. See the equations. Some important relations.
See the equations. Sommerfeld-Wilson, 1915, 1916, Sommerfeld 56 and Wilson 57, would retain the quantization on angular momentum of the original Bohr model, but now have electron motion on elliptical orbits satisfying an additional radial quantization condition.
See the next equation, where p is the radial momentum canonically conjugate to the radial coordinate q, and t is the time for one of the orbit. Interestingly, the fundamental quantization on angular momentum is revealed in even the simplest models. We will see why angular momentum should be so readily quantized, as a direct consequence of canonical quantization, in section 3.2. Note that, as discussed in section 3.5, the mere existence of a wave description of matter, by Benedict's theorem, will give rise to an uncertainty relation, from which canonical quantization can be shown, Leonard, 58, and thus angular moment quantization, shown in section 3.2. Stern-Gerlach experiment, intrinsic spin, 1922, 59. The Stern-Gerlach experiment was conducted in 1922 and it revealed that particles possess an intrinsic angular momentum that is quantized. Electrons, in particular, have an intrinsic spin of plus or minus 1 divided by 2. In Book 5 Quantum Field Theory, 15, we will see that electron spin properties are merely due to matter being spinorial, which is a representation of the Lorentz group along with the more familiar vector fields that underlie gauge forces.